Now, there's a particular set of technologies that I have been long excited about, and they surround knowledge graphs. And I've always thought they've been interesting. I've always thought they've been powerful. But what I'm seeing in today, in the age of AI, they are going to transform things. Now, what inspired me to write this talk to begin with was a paper written by a man named Juan Cicada. And he authored this in 2021, this paper called A Brief History of Knowledge Graphs' Main Ideas. And that just opened a rabbit hole for me. And I went deep into this, reading so deep into it. And I reached out to a friend of mine. He is a science fiction author. He is a brilliant man. And he was an outstanding research partner, Bill DeSmit. And I hope to see him again soon, actually, hopefully this year. He's been doing things like conversational agents since the 1990s. He's a brilliant thinker in the knowledge graph space, and honored to call him a friend, and I was very happy I got to collaborate with him on this project. And finally, a word about me. You know who I am. I'm a magician. I'm a hands-on software architect. Sometimes I call myself a knowledge graph grease monkey. And I live somewhere in the intersection of magic and technology. Now, knowledge graphs are poised to dramatically change the landscape of the software we write, particularly in the age of AI. So any education in this space, just awareness right now. This is what I want to give you, a little bit of awareness and a little bit of an appreciation for how we got here. But it's going to give a huge advantage to forward-leaning software engineers. So we're going to talk about knowledge graphs, where we are, how we got here. And in a moment, I'm going to start with where I came from, but I want to show you what this can look like and how you can begin to see the power of this. This is a brief video that I showed in my previous talk, the architecture patterns for AI-powered applications, but it's even more relevant here because it's all about connecting your organization's data to language models in a way that is potentially very different from RAG. Not that one replaces the other or one is better than the other. It's just more tools that we have at our disposal. So this was a quick demo that was put together very early in the days of GPT-3 by another knowledge graph grease monkey, guy named Tony Seal. And here it is.
GPT is a super powerful tool, but to really make it useful, we need to find a way of connecting it back into our own information. What most people haven't really figured out yet is that while GPT has been learning by looking at all of the text on all of the different pages on the web, at the same time, 40% of those web pages have got little islands of JSON-LD embedded within them. These JSON-LD islands form two things. Firstly, a graph, so we can ask a question of GPT and then we can get the data back in a graph format. But secondly, they're like little anchor points that we can link our own data back into. So GPT will come back with information, but if we adopt the same model internally and use JSON-LD within our own organization, then we can blend our data in with the data that GPT is holding, linking it into information that, for obvious reasons, we would want to keep private to our own organization. So we can ask general questions using GPT's general intelligence and link them back to specific data that we hold internally. This pretty much applies, I think, to any organization. And sometimes you will need to extend the model in schema.org. So yes, have all your data available in JSON-LD. Yes, use schema.org as your basis, but have your own internal version of schema.org hosted within your company. That lets you build your own models, but when you build these models, make them extend the ones that GPT is being trained on out on the web. I think the potential of this technology is actually quite vast. Imagine that, not like this toy example, but in a real example, you have all of the data available from all of your various different systems. They're all linked together and they're all linking back to GPT's general intelligence. Perhaps stop and think for a second about the disruptive potential of this to your organization and others.
Very exciting demonstration. And like he says, just take a moment to think about the disruptive potential of all of this. this kind of builds on what I was talking about in the keynote this morning. Those who cannot remember the past are condemned to repeat it. So we're going to talk about where knowledge graphs came from, where ideas around artificial intelligence have come from, but we're going to start with where I came from. I grew up in a very small town in rural Wyoming. It's a state in the United States, and if you don't know where it is in the United States, don't worry. Most Americans don't know where it is either. It was a weird place for somebody like me to grow up. It had a monoculture into which I did not fit. I struggled to fit in. I struggled to be understood. I was generally friendly and outgoing, but I grew up feeling isolated. And I knew there was a whole world outside of my hometown, but I had no ability to see beyond barren, high desert landscape. Now, I was fortunate that I got my first computer in the mid to late 1980s, and it gave me a new world to explore. And at first, I explored outward, played with software, bought things, but this, as you may or may not recognize, is an Apple II. There are no Apple IIs anymore, except in collections and in museums. It is an obsolete platform. And it actually became obsolete right around the time that we bought it, which was exciting. People stopped making software for it, and what software was available, we couldn't buy in stores. So that forced me, instead of exploring outwards, to explore inwards. I learned how to program on that machine. I had a neighbor move in next door to me who became a friend and a mentor. And he was actually responsible for implementing a project called the National School Network Testbed. It was an experiment to look at connecting regular schools, K through 12 schools, to the budding internet. And at that time, it was called the NSFnet. And that gave me an opportunity to connect outside of that town and into the world. And this essay, this fraction of this essay really resonated with me when I read it, because it captured the feelings that I felt at that time. The author says, and then it happened. A door opened to a world, rushing through the phone line like heroin through an addict's vein. An electronic pulse is sent out. A refuge from the day-to-day incompetencies is sought. A board is found. This is it. This is where I belong. I know everyone here, even if I've never met them, never talked to them, may never hear from them again. I know you all. That was written by a man named Lloyd Blankenship, also known as the Mentor. And at that time in my life, if it wasn't computers or magic, I wasn't interested. I remember when I was going into college, I was studying physics, but I wanted to take some classes in IT. I thought that would be an easy A, because I'd been in this world for as long as I could remember. And then I was blindsided by a question early on in this class to gauge where we were. And I thought I was going to just ace this. I was going to smoke it. What is the difference between data and information? I didn't know the answer. It angered me. Like, aren't these two synonymous? Aren't these the same thing? Data, information, different sides of the same coin? Because in my world, technology was an electronic frontier to explore. And in much of the rest of the world, computers were a tool to solve business problems, and information is central to almost all of these problems. And then there was the next question. What's the difference between information and knowledge? And this is all beginning to feel like a very navel-gazing exploration of the question, how many angels can dance on the head of a pin? And I now understand that there is a world of difference between data, information, and knowledge. And in the first half of the 21st century, knowledge is becoming as important to businesses as information was in the later part of the 20th. So let's break this down. This is data. Maybe you work for a company and they say, we're a data-driven company, right? You've heard this. People say this. Here's some data. We make data-driven decisions. Here's some data. What decision should I make? It's meaningless. What if we add some context? By the way, these are Fahrenheit because we haven't figured out how to use the more useful units that the rest of the world is using. But you can see these are temperatures. And so So information is data with context. And this is why I get so frustrated when organizations talk so much about data, because they want information, but they just sort of assume the two are synonymous, even though we are always writing the code to add that context in again and again and again and again and again every time we consume it. And then there's knowledge, but I still can't necessarily make any decisions with this. So it becomes knowledge when we add multiple contexts. And now I can decide what to do on a given day. Multiple contexts allow for informed decisions. Now, we innately do this. Multiple contexts and implicit axioms. And it's easy for us. It's difficult for machines, even with our very, very clever language models. Now, we have humans in the middle, but it works, but it's slow. So let's go a little deeper. Knowledge, which we understand now, and graph, the data structure. This is where we can work in multiple and dynamic contexts. When you start to play with knowledge graphs, you realize that you can change your context at will. You can look at the data through one lens from one context, and then you look at it again in a different context and you get different answers. And it becomes a different form of useful. We can start doing things like inferencing. But, to really explore this space and what is knowledge and what it is to explore, what it is to understand something and what it is to do inferencing and reasoning, we really have to ask questions because modern business problems require access to vast and complex knowledge. So people have been asking this question for a very long time. The philosophers grappled with this. Metaphysics, logic, they formalized some answers, and the echoes of the philosophers from thousands of years ago continue in almost everything that we do. And you'll see how this comes full circle to what matters to us today in a few moments. So we'll explore a couple foundational ideas that informed all of this future work. And we're going to start by going all the way back to ancient Greece. Now, I will say this, if you are a professional level philosophizer, then you're going to probably find my survey of the work too brief. If you're not, you're probably going to find my survey not brief enough. And I'll be honest, this is probably the level of philosopher that I'm actually at. Yep. We'll start that again. Ready to unmute? There we go.
Dust. Win. Dude.
That is, of course, Socrates. But since he's currently busy helping a couple high school students pass a history final, I'll start with one of Socrates' students, a man named Plato. Plato was born in Athens at 428 BCE. He's a student of Socrates. He taught Aristotle, and he's best known for the Republic and his theory of metaphysical forms. So metaphysics is the study of consciousness, existence, and reality. What is? What can we know? And Plato's work in this area led to attempts to define knowledge. And on the individual level, he defined knowledge as justified true belief. We call that the tripartite test. That is, for a person to know proposition P, it must be true. The person must believe that P is the case, and his or her belief that P is the case must be justified. Let's try something. I'm going to tell you a fact. I am married to Kate. This happens to be true. I can justify this with a marriage certificate. And if you believe me, you now know this fact. We've got audio. I know this reference isn't going to land, but this is a very important part of my childhood. Anyway, let me tell you another fact. My best friend is Draco. Now, this happens to be true and justified, since I happen to be the ultimate arbiter of who my best friend is. Consequently, if I make this statement and you believe me, then we meet the three-part test. This is something that you now know. Now, imagine that's all you know about me and Draco and Kate. Yes, this is his real name. Yes, he's a magician And yes, he's the OG Draco before all the Harry Potter. But let's see what else you know. Is Kate married to me? Yes. That fact is also true, and you probably believe it. But how did you justify it? Well, the marriage certificate, you're right. But I only told you that I'm married to Kate. It's right. Marriage is bi-directional. And it's one of those truly remarkable things about knowledge versus information. The fact that knowledge is information with multiple contexts allows us to know via reasoning many facts inferred from a single fact. In other words, one single entry in your knowledge graph, you can infer a bunch more. The whole becomes greater than the sum of its parts. How about this? Am I Draco's best friend? You're not certain? Yeah. You know, we can apply reasoning to infer the answer to the first question because we know that the marriage relationship is symmetric. It works both ways. But the behavior of the best friend relationship is not always symmetric, so we can't reliably infer an answer to the question. So what we're doing is we're taking knowledge and we're applying logic to it. That inference is based on logic. And although you've maybe never formally expressed the semantics of the married to relationship or the best friend of relationship, these are just things you intuitively know. And so for the philosophers or the knowledge systems, intuitively know is not enough. You know, and when you say, well, it works that way because it works that way, they're going to say that's circular reasoning. It's unacceptable. And if to know is to have a justified true belief, then justifying knowing because I know doesn't compute. And what this means is when we're building knowledge systems, it's more than just the storage and retrieval of facts. And in fact, you can see how you can start to infer new knowledge, and it gives us a new framework for knowledge to be justified. So for a lot of human history, our ability to reason was present, but we didn't understand it very well. We had implicit rules, we had heuristics, but they were all functionally invisible and difficult to define and articulate. But philosophers finally got to work in effing the ineffable and started formally defining logic. Now, one of the first people to start thinking about this stuff was another philosopher named Heraclitus, born in Ephesus, 540 BCE, which is now, I think, a part of Turkey. And we're going a little further back. Now, Heraclitus is best known for his cosmology, and he had this idea of the universe being, the fundamental form being fire, but there's not a lot was really known about him, because a lot of his work got lost. But he's also considered to be a pre-Socratic as a philosopher. We have different groups of philosophers, and he's part of a group that we call the pre-Socratics. Isn't it depressing that your entire work is summed up as, yeah, you're just one of the guys that did the stuff before the real guy came along, before Socrates came along? But he did some of the earliest writing about logic, or logos, in the ancient Greek. So logos refers to the appeal to reason that relies on logic, reason, inductive, and deductive reasoning. And it's part of different forms of rhetoric of an argument, what makes something valid. Logos, ethos, and pathos. And I've got a great quote here. The logos holds always, but humans always prove unable to understand it, both before hearing it and when they have finally first heard it. For all things to come to be in accordance with the logos, humans are like the inexperienced when they experience such words and deeds as I set out, distinguishing each in accordance with its nature and saying how it is. But other people fail to notice what they do when awake, just as they forget what they do while asleep. Another philosopher. Now, Plato did more work on logic. Plato, he did some early thinking on logic, and this in turn influenced, but he said this: what is it that property that can be called true or false? What does it mean for something to be true or false? What is the nature of the connection between assumptions of a valid argument and its conclusion? What is the nature of definition? These are actually really important questions, and when you start to dive into them, they become very difficult. And Plato's student was Aristotle, and the logic of Aristotle, and particularly his theory of the syllogism, it had enormous influence on philosophical thought, Western thought, Aristotle was the first logician to attempt to systematize analysis for logic and of syntax, like nouns or terms and verbs. He was the first formal logician, and he demonstrated a lot of principles of reasoning. And he thought. He sought to show the underlying. He thought to show relations of dependence which allow inference. He was the first to deal with principles of contradiction and did a lot of this in a very systemic way. Other important work on logic was done by the Stoics, and the Stoics did a lot of work on conditional logic. But we're back to logos. Logic provides formalisms that allow the definition of objective truth. These ideas of logic found their way into our ideas of logic. And it's important because it gives us a new type of justification for truth outside of our own subjective experience. It gives us a framework for defining collective truth and collective knowledge. And then from there, we start to define the world. Like, what exists in the world? And that becomes an astonishingly difficult question to answer. There's a really great video by Vsauce entitled, "Do Chairs Exist?" And that sounds like an absurd question. And then you watch this video, and then you're not sure. So we have this idea of ontology. And by the way, ideal in ontologies now. Ontologies are central to knowledge graphs because what you're trying to do is to define the things that exist in our world. Not just the world globally, but in our enterprise world. What are the concepts? Where do they start? Where do they end? We have components that make up things that we buy and sell. We have this thing right here, this remote. Is this one thing or three things or many things? And it depends. It depends. So this is where the philosophy of ontology and semantics start to enter into all of this. Ontology addresses questions like how entities are grouped together into categories, which of these entities actually exist on a fundamental level. Ontologists try to determine what the categories or highest kinds are and how they form a system of categories to put all this together. But if we're defining and classifying reality, then the field of ontology gives us a framework to do this, and semantics allows us to be precise in our descriptions and the behavior of ideas and relationships in reality. And then we have a more contemporary philosopher entering the stage. This is John Locke. He was in England in 1632, and he made important contributions to the field of semantics, particularly in his essay, An Essay Concerning Human Understanding. And he started to put some of these pieces together. Okay, we've been talking about philosophy. I've already had two people walk out. Who cares about philosophy? Well, this guy did. This guy's the reason we're all here. And regrettably, I would wager nobody knows who he is. Oh, one? Here. Information theory. You're right. Hey? Say that one more time. That might be. I'm not sure. But this was a student in. He was a student in the 1930s at the University of Michigan, and he was studying engineering and mathematics. And he decided, you know what? A dual major in two highly technical fields? I'm not busy enough. So he started taking a lot of elective classes that he didn't need to take. He had that quality of curiosity I was talking about this morning. So he takes a philosophy class, and he learns about an obscure 1800s philosopher who wrote this very underappreciated paper on his approach to logic. He was trying to take the ideas of the ancients and formalize them in a more simplified, direct way. He said, he basically said, instead of all this thoughts of syllogisms and forms and nouns and verbs and all of that. I'm just going to boil it down. I'm going to represent what is true with a 1 and what is false with a 0. And he built a system of logic around that. That person you probably have heard of, George Boole. He was born in England in 1815. In 1854, he published his seminal work on investigation laws of thought. And the book's purpose was to investigate the fundamental laws and operations of the mind by which reasoning is performed. And he did a lot of interesting things with this. But when Claude Shannon learned of George Boole's work, an entire system of logic based on 1s and 0s, Shannon's master's thesis was on electronic switching circuits. And at that time, if you've ever seen electromechanical machines that don't have integrated circuits, don't have processors, they have wires and motors that do math. It's amazing. It's astonishing. The leap, how that changed everything. And this is why I have this. This is why I have this laptop. This is why we have careers. Because he figured out how to make digital electronic computers a practical reality. And, people were blown away by what he accomplished. They said, how did you do this? Why didn't we do this sooner? And Shannon said it just happened that no one else was familiar with both fields at the same time. And that was where the innovation came from, connecting disjoint ideas in novel ways. And so this is another reason that curiosity is so important. But we fast forward a couple of decades, and we're getting into the first real thinking about artificial intelligence that published in Mind, a quarterly review of psychology and philosophy. Alan Turing published Computing Machinery and Intelligence. See, at that time, most computers were just programmable calculators. But Turing had already moved on. Turing basically conceived that a computer could be possible. Claude Shannon figured out how to actually make it happen. And while everybody's playing around with these new, very noisy, very expensive calculators, Alan Turing is like, let's see if we can figure out how to make them think. I talked about these gentlemen, Alan Newell and Herb Simon, and they created logic theorists. But once they started playing with it, they knew they were onto something. In fact, there's this quote right here. He said, I had such a sense of clarity that this was a new path and one that I was going to go down. I haven't had that sensation very many times. I'm pretty skeptical, so I don't normally go off on a toot, whatever that means. But I did on that one, completely absorbed in it without existing with the 2 to 3 levels of consciousness so that you're working and you're aware that you're working and aware of the consequences and implications. The normal mode of thought, no, completely absorbed for 10 to 12 hours. And this was Alan Newell. And this was how I felt when I started playing with knowledge graphs and started exploring these ideas. And so after they built that first program that I was telling you about, Logic Theorist, where they proved that a machine could perform tasks hereto considered intelligent, creative, and uniquely human, they generated a second thing. And I mentioned this in the keynote. They developed General Problem Solver in 1958. And they realized that there were challenges with finding solutions in a vast solution space. But it turns out that there's more research that needed to be done. Fortunately, Dijkstra was doing that research. And this put us on the road to artificial reasoning. This is the beginning of the journey that has led to us today. And part of me wishes that you could go back in time and show some of these people how far we've come. I think it would just blow people's minds to sit in some of the sessions, showing things, giving you the tools and the quick starts and everything you need to do astonishing things that so many of these people in history just dreamt about. But it was a journey. It was a road. There was this guy, Richard H. Hitkins, developed the notion of a semantic network. So he built on the work of the philosophers. And he realized we have to start to connect things and how they relate and what they mean. And it's a knowledge base that represents semantic relationships between concepts in a network. And it's often a form of knowledge representation, and it's key to modeling the complexities of the real world. Now, there's a lot more to do, but, today we stand on the shoulders of giants, and the modern knowledge graph is becoming a practical reality that's ready for production, even though it was a journey to get there. Information retrieval is another key development. In the 1960s, we started thinking about information retrieval from unstructured sources. We have this for free now. All these open source information retrieval systems that are orders of magnitude better than anything anybody could have imagined. There was a guy named Bertram Raphael. He developed something called SIR, S-I-R, and that was a computer program for semantic information retrieval. That's what SIR stands for. And it demonstrated the rudimentary capability to understand semantic information, and he was demonstrating procedures to extract semantic content from English sentences. And one of the biggest challenges, though, that we had was modeling knowledge, modeling the meaning of the data. And so as we're moving into the 1970s, we saw a lot of improvements and refinements to Richard Richin's concept of these semantic networks. And the ideas had incredible potential. The foundations, though, were weak. They needed refinement. And in 1975, William Woods published a paper, What's in a Link? Foundations for Semantic Networks. And he outlined the weaknesses of the model and the need for more formal understanding of classes, links, and properties. And this push continued work in this era that would be crucial for modern day knowledge graphs. Another key idea that was developed in the 70s was Marvin Minsky's concept of a frame. And he introduced this in his article, A Framework for Representing Knowledge. So a frame is an artificial intelligence data structure used to divide knowledge into substructures representing what he called stereotype situations. Frames are the primary data structure in a lot of the previous generations of artificial intelligence frame languages, and they're stored as ontologies and sets. And frames are still an extensive part of knowledge representation and reasoning schemes. They were originally derived from semantic networks, and they formed part of structure-based knowledge representations. Now, 2 years after Minsky introduced frames, a guy named Patrick Hayes recognized that frame networks could be formalized using first-order logic. And he published a 1977 paper in defense of logic. And that would later introduce Brockman and Levesque to identify a solvable, a tractable subset of first-order logic, which would be the first development in description logistics, or logics. The 1960s, going back a little bit, we also saw developments in the first database management systems and programming languages that could handle data. So Charles Bachman developed the integrated data store, which cemented data independence from the programming logic. That was a big development. And in fact, it was so important, it earned him a Turing Award. And we had high-level languages now, like Fortran, that allowed a lot more intuitive and natural ways to interact with logic and data. Now, it was a couple more decades before the formalization of the fundamental trade-off between the expressive power of language and the computational complexity of reasoning. And we saw that in Bachman and Levesque's paper, the tractability of subsumption in frame-based description languages. But by increasing the descriptive and the expressive power of a language, you start paying in computational efficiency. That's still a problem we have today, but we have super powerful GPUs, and we have seemingly limitless funding and a lot of energy going into it. And we've seen how far we can take this with modern computing. But this led at the time to a flurry of activities to find trade-offs along the expressivity continuum to find that balance where we could start getting value right away. We got a new family of logics called description logics. And there are a lot of different systems that stood out, KL1, Loom, Classic. And in addition to description logic, there was another formalism being developed at the time, F-logic, which was, again, heavily influenced by objects and frames. And even though these early logic systems didn't receive massive industry uptake, at the time, it showed that logical reasoning could be implemented in tractable software. This was a solvable problem. Again, this is the journey that got us to language models and AI and the knowledge graph stuff that is starting to take shape. And in fact, these ideas right here eventually became the underpinning of the most widely used ontology language, OWL, and the semantic web and linked data. But there were some steps that we had to follow to get there. We had to find ways to express complex relationships. We needed better storage. We needed better logic programming. So in the years before I came into this world, we started to see data revolutions. Obviously, computers were here to stay. They were starting to show up in more places. Technology needed to adapt. And we started seeing early database management systems that originated from Charles Bachman and IDS, and they were very massively expanded on by Ed Codd in his 1970 paper, A Relational Model of Data for Large Shared Data Banks. His ideas still matter today. We still follow all of this today. I in the keynote this morning, I raised your hand if you use relational databases. Almost every hand went up. This is where it started, and his initial thinking, it never existed before. Like, we had to invent all of this stuff. In fact, this is the paper. And so in this paper, Codd described the use of relations as a mathematical model to provide representational independence and allowed programmers to start to work at higher levels of abstraction and start to ignore the physical storage mechanisms. You know, at this time, you had to write the code to access the disk to go, and you had to build your own B-tree indexes. Today, I just say create index, da-da-da. But it's just kind of amazing seeing how far we came. Nope, what just happened? There was another individual, Peter Chan, introduced the entity relationship model, which we still use again today. And he focused on modeling data based on entities and their relationships, as the name would suggest. And at this point, the relational databases were born. And you know, SQL, it used to be called SQL. And for some reason, I think they had to change it. It was SEQUEL. And I think there was a trademark issue or something like that. So it became SQL, but we still say SQL, except for the Primogen. I think he says squeal. But it was right around the same time that relationship databases were reaching this level of maturity. John Sawa was exploring the idea of conceptual graphs. How are different concepts related? And he was finding this as a way to map natural language queries and assertions to a relational database. And we started to get hints at how data and knowledge might begin to intersect. And one of the most influential events of the 1970s was the workshop on logic and databases in 1977. And this was really the birth of the logical approach to data. And it has impacts today in the knowledge graph all over the place. One of the most interesting developments of that era was the introduction of logic programming. When I talk to people, when I do training on knowledge graphs and things around that, I start demonstrating RDF, the resource description framework, which is a foundation for a type of knowledge graph. And what a lot of people say when they look at it, they say, this looks a lot like Prolog. And this is, in fact, where these ideas were conceived in Robert Kowalski's paper, Predicate Logic as a Programming Language. And Alan, I don't know how to pronounce his last name, but the creator of Prolog. And so you start seeing how these ideas start to take shape, and then things eventually begin to accelerate. So in the academic realm, there were early efforts to combine logic and data with logic programming over relational databases. But since logic programming focuses on defining functionality without specifying algorithms, optimization became crucial. And we started to discover that optimization in this context was way more challenging than relational query optimization. And that led to the development of deductive database systems that were actually doing primitive forms of reasoning. And they were extending relational databases with recursive rules and optimizations. And then we got Datalog, which is a programming language or a query language. If you were in my logseq class, there are basic, very, very simple queries for certain things, but you can also write Datalog queries in my personal knowledge graph in logseq that I was talking about the other day. Datalog is a Prolog subset, and it gave us a more solid foundation for logical programming. And that, with the formalization of relational databases, gave us language for deductive databases, databases. And we started seeing things that were called active databases. But semantic networks are clearly graphs, and relational databases were hitting limits in this space. So we needed to deal with the fact that data comes in different shapes. Data comes in different flavors. We have data heterogeneity problems. So graphs started to be investigated as representations for object-oriented data. They were, we were starting to get graphical and visual interfaces. We had hypertext, things like that. And we started seeing graph query languages. And this is also right around the time that the entire paradigm was starting to shift. But 1970s, the computing industry was reaching the mainstream. It was starting to become pervasive in business. Capabilities were increasing rapidly. Cost was going down. It was a turning point in history where enterprises were beginning to realize that if we don't have computers, this is make or break for us. And it would be harder and harder to be competitive without this stuff. Just like the same set of revolutions with the web a couple of decades ago, we saw that story again, and we're seeing it now with AI. But there was a generation of people like me who became fascinated by these machines and their potential. But at that time, the cost and complexity put them completely out of reach. But smart individuals, and in fact, I was sitting right there in this room earlier today, and I was talking about this guy right there. Our keynote speaker this morning, Nicholas, was talking about this guy right here. They wanted to figure out how to build their own computers. There's a really great book that chronicles all of this. This is probably my favorite piece of history from all of the last 75 years in computers. It's called Fire in the Valley, and inspired a film called The Pirates of Silicon Valley. So the first personal computer is this right here. This came from a company called MITS. It was the Altair 8080. It was sold as a kit. Now, this is a beautiful thing. There's no keyboard. There's no monitor. There are switches, and there are lights. This is how you program it. This is how you do input. This is your output. Figure it out. Do something useful with it. People love these things, and they'd write little programs that would make the lights flash around, chase around, do different things, do basic calculations. They weren't sure what to do with it. And one day, there was a group of enthusiasts it was called the Homebrew Computer Club. And somebody brought one of these in. Oh, by the way, there's also no storage. No tape drive, no disk drive, no hard drive, nothing. Which means when you turn it off, it's all gone. Everything's stored volatile memory. Maybe a kilobyte of volatile memory. But a guy brought this into the Homebrew Computer Club, and while they were doing their lectures and people were talking, the guy sitting there furiously flicking switches, loading another register, putting another byte of instructions in there, pure machine code. And I think at one point somebody tripped over the cable and an hour of work was lost. He started all over again. And before the whole thing was done, he takes a little transistor radio, he puts it on top of it, and he runs his program. And the radio starts playing music. Because he was coding loops with different delays and different speeds. And it was causing interference that little radio was picking up. And the first time anybody actually did something that appeared useful with this machine. But demand for even though you couldn't do anything with it, imagine loving computers as much as you and I do. And this was the state of the art. Like, it's hard to fathom now, but people were camping in parking lots in New Mexico for weeks to be the first to get their hands on one of these. There were a couple gentlemen going to Harvard University, and they saw this thing came out, and they immediately dropped out of college. They're like, it's happening. The future is happening. I'm going to show you a clip from the film, The Pirates of Silicon Valley.
Bill, the revolution starting without us.
Bill and Paul Arlen had known each other since they were kids, and if the word passion entered into their lives, it was for one thing: computers. Especially this one made by some guy in Albuquerque, of all places. What is this? Aeon for engineers? Oh, geez, the Altair. Am I missing something? I mean, Miss October I can understand, but what is this? This is better than Miss October. Oh, God.
The article says that they need someone to figure out a computer language for us. Right now, it just sits there and blinks.
So Bill Gates and Paul Allen dropped out of college, said, forget the degree. We're going to found a company. They decided to call it Microsoft. And right around the same time, Steve Jobs and Steve Wozniak founded Apple Computer. And see, Steve Jobs' engineering brilliance made the Altair obsolete overnight. And Apple was almost single-handedly responsible for launching the personal computer revolution. And it almost didn't happen. It almost didn't happen. Check this out.
Because our universe folded, that our universe folded.
I know, but I still don't think I can build them. You know I work for Hewlett Packard sometimes, right?
Yeah, and?
And my dad pointed it out, they get first chance in anything I invent. What? Well, I can't help it. It's right there on the paper I signed when I started working there.
It's damn it, war, son. To get our shot, our destiny, and now we got to turn it all over these businessmen.
Steve, it is Steve. Yeah, Steve, you say that this gadget of yours is for ordinary people. What on earth would ordinary people with computers?
Steve Jobs paces and waits to find out the future of everything. But Hewlett Packard didn't seem that interested in personal computers. And a recurring theme of this timeline is that the revolutionary possibilities of technologies aren't always immediately obvious.
What? What?
They hated it. You shouldn't say it. No,
And not too long after that, they got their first round of funding and the Apple II was born. But it didn't receive wide adoption until the personal computer had its first killer app. Something that was so important, so valuable, that you had to have it. And that, does anybody know what that is? The first killer app for the personal computer. Oh, what's your name? Red. Yes. I've done a lot of talking this week. My mouth barely works. You're absolutely right. VisiCalc, the first spreadsheet. And it single-handedly transformed the computing landscape. It allowed the operator to rapidly manipulate data in context. And there was no denying it anymore. Computers could do so much more than mere computing. And computers started to move out of machine rooms and onto almost every desk. And we started getting information systems. But we would build them one at a time as we had a problem to solve. And now we're in an era where we need to connect that information. But we have silos. I had a client a while back, and they asked this question of me. What do I currently hold in my warehouse that isn't a current product or used to manufacture any of our current products? Well, they were having a hard time answering that question because they have a part lifecycle management system, they have a warehouse system, they have a sales system, and they have a product catalog. And the answer spans all of those. And they were just having a really hard time doing these recursive hierarchical queries because we have to jump all over the place to get these answers. And I helped them build the foundation, represent all of this in a graph where it all connects. And then they said this, we have another question. Based on our current delivery commitments, inventory, and procurement lead times, what sales deadlines are in danger of slipping? And they had their PLM, their warehouse, their sales, but now they also have to integrate their procurement system in addition to the product catalog, and their supplier catalog, and their supplier inventory, and their shipment tracking, and production lead times. But we looked at different ways we keep doing this the hard way. And what we need to do is we keep doing this the hard way. I saw this a while back in relation to something like this. Because hard is subjective. I love this. Everybody's pushing their blocks, and this guy's like, I'm going to chisel into a sphere and roll it off. Work smarter, not harder. And this is kind of how we approach this. It's like, well, this is the obvious solution. And then somebody commented below, that guy is delivering a useless sphere when cubes were required. And this is kind of how we're approaching data integration right now. We keep giving data when information is required. And the way that we build this is by point-to-point systems, point-to-point integrations. We build all of our APIs as one of one little snowflakes that nothing else is like. Even though we use HTTP, we've got some common things, but otherwise, it's always different. Because in the beginning, we had two things to connect. Oh, that's okay. I'll just write a little thing, connect it really quick. Done. Oh, we have a second thing. Well, I'll write one more. That's cool. But this is where we are. We are here. This is our ability to write these things. Actually, this is probably spiked up a little bit. And this, off the page now, is where the amount of information we are creating. And this is where knowledge graphs are becoming essential. See, we are still applying thinking from this era into a problem that is in this era. And this is where we're starting to get to the magic of knowledge graphs. It won't scale. And the thing is, we solved the problem of web scale integration in the 90s with something that was barely more advanced. Now I'm going to scroll back. Barely more advanced than this. And it reminds me of that scene in Iron Man 2, because we're still struggling with this. And part of me wants to say, Tony Stark built this in a cave with a box of scraps. But it's time to learn these lessons. So we got the dawn of the web, and everybody got so excited about the World Wide Web, where we got global web scale interoperability of documents, that there are no snowflakes there. Your web browser can talk to any web server. It doesn't matter if it's WebSphere or IIS or Nginx or you name it. It always works because we solved the problem of web scale integration of information. But the vision was always to include data and our software systems as well. And so even though everybody saw the web and they're like, this is really cool, we're linking the documents, that's awesome. Tim Berners-Lee was sitting there thinking, wait, that was just part of it. That was this much of the vision. But everyone's like, no, thank you. But they kept working anyway. And they developed a new set of standards called the Resource Description Framework. This is my website version of it. It is, every now and again, people look at my website and they say, Michael, your website is not ready for prime time. What they don't understand is my website is a love letter to how terrible the web was in the 1990s, if you remember that. But you look at this, it's pretty standard HTML, some Windows 95 style pop-ups that are spawning the screen, if you've ever seen that. But this is kind of the vision that they were seeing. There's a lot of, this is my webpage, it's what a human sees. There's a lot of human-focused information. But the vision was to connect the data as well. And we wanted this document to be useful to a human or a machine. But on this site, there's actually a ton of structured information. If we look at the source, you see a lot of meta tags popped all over the place. What I found, what you can do is I can actually span a property. I can assign a property to something like a span. So this span has stuff in it. Or this anchor tag has a property. This span has a property, Great International Developer Summit. So, or it has a value of Great International Developer Summit, and it has a property of a name. I'm actually describing a graph of knowledge. I'm assigning properties to spans and links and things like that. So right here. I forgot I had a zoom thing. And so what this does, this actually expresses an RDF fragment. In other words, it expresses a graph fragment. This is one way to express this, one serialization. Oh, I'll go back. Sorry. We were here. Yeah. So this is just a graph fragment. And I have all these graph fragments in my document. I can also embed metadata that's not displayed. And again, this is just all more graph data. And in fact, if I take this data or take this raw web source, just the HTML, I put in a tool, this is a glimpse of the data there's a knowledge graph in my website. Now, a lot of people don't do this kind of thing anymore. Actually, no, we do a lot of this. 50% of the index web has data like this. These days, it's usually expressed as JSON LD, which is another graph serialization. But 50% of I think I said that. 50% of the index web has data like this, a very rich set of data. And we get interesting things in here, like, I have the website itself. I've got this idea of Micheal here, this edge in the Micheal, that is Micheal. And in fact, we see other places where we reference this graph fragment because Micheal is the author of the document. I'm speaking at these conferences. Now, when you start looking at this stuff, it probably starts to sound like I'm talking about the semantic web. And if you were around when people started talking about it the first time, we haven't been talking about it so much in a while. This is 2020 down there. It kind of bottomed out. And the thing is, when we first learned about the semantic web, almost nobody cared. But suddenly with AI and knowledge graphs and everything else, all of this stuff is coming back into meaning. How much time do we have left, by the way? 1 minute. I got so excited telling this story. But the thing about knowledge graphs is that what people want is answers. Like, what time is sunrise in Helsinki next Thursday? It will tell me. And we want, this is why Google puts things in here, because we want answers and not hits. When we connect the data, we start completely changing the landscape. Instead of doing this point-to-point integration, we have knowledge graphs are all about taking heterogeneous data and being able to connect it naturally as a property. The fact that the data connects is a property of the data itself. And that's why taking this kind of knowledge graph approach or a data-centric approach starts to completely change the way we think about systems. Now, people are getting excited about things like MCP right now because we're showing that I can build one more of these 124,750 integrations. But when the data just connects, really amazing things start to happen. There was a project years ago, something called DBpedia, where they wanted to turn the documents in Wikipedia into graphs. And because the data connects, other people can connect their data sets. And more people got involved, and more people got involved, and more people got involved, and more people got involved. All of these data sets are created by volunteers on their own time. Nobody has to coordinate. That data just connects. And what we have is a whole set of standards that are available to us now that solve a lot of these problems. And we have the answers now to do web scale data integration. And so when you really start seeing the power of this stuff, when things really start to take off, you end up with, it's not even a fair fight. But I know we're out of time, but the key thing I want to go back to now is the knowledge graphs today allow us to connect all of our information at a scale that the old ways aren't helping us. The standards and technologies that we have that are mature at this point are solving key problems to enable agentic systems, giving us holistic views of our data, giving us capabilities like this. But to kind of wrap all this up, we have major breakthroughs that took time, took effort, spanned a lot of different disciplines, and it's really leading to a very exciting future. Now we have Graph RAG. Now we have the potential for web scale agent integration. It is a cool time to be alive, and I am so glad that I am here with you instead of 50 or 100 or hundreds or thousands of years ago just dreaming about these things. I hope this was a useful thing. Thank you.